Hello class. So back once again, chapter 15. I'm going to do two homework problems that are similar to your last two homework problems in your homework set. I think it's 14 and 15. We're going to do problem, let's see here, I had it written down, 15.37 from your book. So problem number 37 from your book is what we're going to do, right? Now these ICE tables are not going to be going away, and I'll explain that here in a moment. I'm going to have a little bit of trouble fitting this all on the board, but I'll make it work. So 1537, a mixture of 0.1 moles of nitrogen monoxide, 0.050 moles of H2, and 0.10 moles of H2O are placed in a 1 liter vessel at 300 Kelvin. The following equilibrium is established. So I'm going to write down our chemical equation here. Again, it's problem 37. We're going to have 2 nitrogen monoxide gas plus 2 H2 gas. It's going to go reversibly. 2 N2 gas plus 2 H2O gas. Right? That's our chemical equation. And then it says at equilibrium, the concentration of nitrogen monoxide is 0.062 molarity. And it asks, calculate the equilibrium concentrations of H2N2 and H2O. So like I told you, this problem involves an ICE table, okay? I would normally write out all the information on the board, but to save space, I'm not going to do that, right? So again, I'm going to use an ICE table. Initial, change, equilibrium. So we're going to make a little table here. Again, ICE, just like that, right? I'm going to make it into a box. Help myself out here. All right, so here's our ICE table. Again, initial, change, equilibrium, right? Standing for the core, the concentrations, right? So our problem says our initial concentration or initial starting amount of nitrogen monoxide is 0.10 moles. Well, it says it's in a 1 liter vessel. So that's 0.10 molarity. So I'm going to put that in here. So initial for NO is 0.10 molarity. Right? I just leave off the capital M just to make things simpler. We have 0.050 moles of H2. Again, 1 liter. So that's 0.050 molarity. And 0.1 moles of H2. Again, divided by 1, that's 0.10 molarity. Again, I'm leaving out the M. Now, it didn't say anything about an N2 starting concentration. So that is 0. Okay? So initial or starting concentrations, this is what we have. What else does it tell us? It tells us at equilibrium, the concentration of nitrogen monoxide is 0.062 molarity. Nitrogen monoxide at equilibrium is 0.062 molarity, is what it says. Okay? Now, we want to know, it asks, what are the equilibrium concentrations of H2, N2, and H2O, is what we want to know. Right? There's a part B that says, then calculate Kc, right? We'll come to that though. So we want to know these 3 concentrations. How are we going to get them? We're going to get them by using this information, okay? So here I have the initial concentration. Here I have the equilibrium concentration of nitrogen monoxide. So the change in concentration has to be 0.10 molarity minus 0.062 molarity. That has to be the change, okay? So do that. Grab your calculator, work that out. It turns out to be minus 0.038, okay, is what the change turns out to be, okay? Remember, 0.10 minus 0.062. That's how I got this, right? I have a negative here because this is the change in. It's, if you go 0.038 molarity, this went over that way, right, is what happened. Well, what about this one? What's the change in this one? Well, this is stoichiometry here, right? This is 2 for 2. Or you could say 1 for 1. So if this went down by 0.038 molarity, this H2 concentration has to go down by 0.038 molarity. It has to. Now what about the other side? So again, let's take a look at the H2O first. Okay, that's going to be the simplest. Excuse me. If the reactants are disappearing, what's going to happen to the product side? The product side is going to be increasing, okay? If the reactants are decreasing, the product side must be increasing. Again, looking at this here, 2NO per 2H2O. It's 1 to 1, right? 1 to 1. The change is 1 to 1. What does that mean? 2 to 2 or 1 to 1? That means that this has to be plus 0.038. I hope I'm explaining so it makes sense. Again, the ratio between the two of these, right? 2 to 2 or 1 to 1. So if this loses 0.038 molarity, we're going to the product side. This has to be plus 0.038 molarity. Has to be. Now let's look at this one here, N2. This is just a little bit trickier. What I'm going to do is I'm actually going to use a stoichiometric equation to figure this part out. So I want to know the change in this, okay? So I want to know molarity of N2, the change. So what am I going to do? I'm going to take this number here, my NO, and then I'm going to use the stoichiometry, right? A ratio. 2NO for every 1 N2. I want NO to cancel, so I set up my ratio here. Just like that. Molarity NO cancels, right? I'm left with the molarity of N2. So do your math. 0.038 divided by 2. 0.019, okay? Now again, note, this is a negative number here, subtracting, right? Notice I don't have a negative down here. This is going away, all right? So since reactants are going away, this side has to be a positive number. So this is plus 0.019. I hope I explained that well. Now though, we can get to equilibrium concentrations, right? 0.050 minus this, 0.038 is going to give us 0.012. Here's 0 plus this is going to give us 0.019. And then here, 0.108 plus this is 0.138. So you now have your equilibrium concentrations. You can write out Kc. And again, like I told you, you have a hard time putting this all on the board. So I'm going to go right here. Again, products over reactants. Products over reactants. Ratio stoichiometric coefficients. So concentration of N2 times concentration of H2O squared divided by concentration of nitrogen monoxide squared divided by concentration of H2 squared. And then plug in all of our numbers. So N2, where's my N2? 0.019 molarity. My H2 equilibrium concentration is right here. Square that one. And then down here, nitrogen monoxide. I have 0.062 molarity, that's going to be squared. And then here, I have H2 squared. Punch all that into your calculator, and according to what I did earlier, I have 653 for my Kc. Okay? I guess if you have questions, email me. We're going to do another example here in a moment with partial pressures, but I hope that explained that so it made somewhat sense. We're going to go on to another problem now. We are going to look at, let's see here. 1540, okay, 1540. All right, 1540 similar, except we're going to be using partial pressures of gases. A flask is charged with 1.500 atmospheres of N2O4 and 1 atmosphere of NO2 at 25 degrees Celsius, and the following equilibrium is achieved. I'll write it on the board. So N2O4, dinitrogen tetroxide, decomposes into nitrogen dioxide. Excuse me. After equilibrium is reached, the partial pressure of NO2 is 0.51 atmospheres. What is the equilibrium partial pressure of N2O4? So once again, we're going to do an ICE table, okay? This one's a little bit easier. We only have 2 chemicals, ICE. And we're using partial pressures, but it works the same way. It works the same way, okay? So initial, 1.500 atmospheres of N2O4 and 1 atmosphere of NO2. Then it says at equilibrium, we have 0.512 atmospheres of NO2. And it asks, what is the equilibrium partial pressure of N2O4? So we're going to do the same thing. We're going to use the change, calculate the change here, then get the change here, and then get the equilibrium. That's what we're going to do. So again, 1 minus something equals 0.512, right? So just take 1 minus 0.52, right? What's that going to give you? That's going to give you 4.88, okay? 0.488. Is it supposed to be a minus or a plus? Well, it's going to be a minus, right? You're going from 1 down to that. So 1 minus 0.488 is going to be 0.512. Okay, so we got the change in partial pressure of NO2. Now, if this partial pressure is decreasing on the product side, what does that mean? It means we're going from products to reactants. This has to be a plus. This must be a plus. Since this is negative on the product side, this has to be a plus, okay? Well, how are we going to calculate this? It's 2 to 1. So again, we're going to calculate the change here. I'm just going to say partial pressure, N2O4 is going to equal, I'm starting off with this, 0.488 atmospheres of NO2. And again, I'm going to use the stoichiometric ratio, right? I want the partial pressure of the NO2 to cancel. So, whoops. Every 2 atmospheres of NO2, there's 1 atmosphere of N2O4. Atmospheres of NO2 cancels, and so you end up dividing that by 2. And what are you going to get? 0.244 atmospheres. That's the change in the N2O4. Okay, that's the change in the N2O4. And if you can just see, it's 2 to 1 to divide by 2, that's fine too. But again, it has to be a positive. So you have positive 0.244. Well, let's calculate this then. 1.500 plus 0.244, you get 1.744 atmospheres for your equilibrium partial pressure of N2O4. That's what it asked for first, was this part right here. I hope I explained it so it makes sense. Then it asks, what is the Kp? So Kp, again, products over reactants, right? Partial pressure of NO2 raised to its stoichiometric coefficient, so it's squared, divided by the reactants, partial pressure of N2O4, raised to the stoichiometric coefficient, which is just 1, and then plug in your values. So I'm going to have here partial pressure of NO2, 0.512 atmospheres squared, divided by the partial pressure of N2O4, the equilibrium, 1.744 atmospheres. Remember, you don't have units, just leave the atmospheres out. Plug all that into your calculator, and I have 0.150 is what I have for KP. Again, hopefully I explained that so it's understandable. Yeah, that's all I have for now. If you have questions, email me. Take care.